All right, continuing on. Number 5. Yeah, so this one's like a baseball. It's spinning and it's moving. And they want the ratio of rotational kinetic energy to translational kinetic energy. So our end goal, we want K rotational divided by K translational. So then you'll need the formulas. K rotational is 1/2 I omega squared. And then K translational is 1/2 mv squared. So we can start plugging in. So then K rotational, I'll write 1/2 I omega squared. And then translational is 1/2 mv squared. So then 1/2 on top, 1/2 on the bottom, those cancel out. So what we end up with is I omega squared over mv squared. Okay. Oh, look. And we have everything, right? Because we know omega, right? There's the omega right there. We know v right here. And we can solve for I using 2/5 mr squared. So then what we'll do is instead of I, right? So I guess I'll just copy this, get myself my room. Instead of I, we'll do 2/5 mr squared. So it'll be 2/5 mr squared omega squared over mv squared. M on top, M on the bottom, cancels out. And then I'll just move the 5 on the bottom. So what we have is 2r squared omega squared over b squared. And then you'll know everything, right? So this is r. And you know omega radians per second. Mine's 199, yours is a different number. And v, mine's 51, yours is a different number. The only thing you have to be careful about is you have to turn your centimeters and meters, right? So mine's 4.37 centimeters. Before I put that into R, you gotta turn that into meters. So I'll just divide by 100 to get meters. So that's 0.0437 meters. And then that will go into R. You'll know omega, right? Mine's 199 radians per second. You know v, they give you that mine's 51 meters per second, and you'll just put that into your ratio, and then you'll get a number, and then you can solve. Cool. So then next question. Okay, so this is like my demonstration that I did in class. Hopefully 4th period we'll get to do it on Friday, unless we cancel school again. But it's like when you pull your arms in, you go faster. And the reasoning behind that is because of conservation of angular momentum. Now, angular momentum is L, and it's conserved. So big L, like Lily, before is equal to big L after. And the formula for big L is equal to I omega. Right, just like momentum is mass times velocity, right? So momentum is angular momentum. Instead of mass, it's moment of inertia. Instead of velocity is angular velocity. Wait, is my mic on? Yes, okay. So we'll just set up our equation so we can solve for the final angular speed of the student. So that is omega after, or final, whatever you want to call it. So L before. So that is I before. So the moment of inertia of the student, the stool before, is like the stool. So I would be like the stool plus the student. So if I do my L before, I'll just make a little chart. So like L before, then L after. So that's I before times omega before. So I before is the student. Okay, it's a stool plus student and the weights. So the stool and the student is 5. So that's 5 plus the weights. So if you're like holding the weights, we can treat that as like a point mass. And the equation for your momentum inertia for like a point mass, right, is just like mr squared. So plus the mass of the weights, right? I'll call that m. My m is 1. Yours is different. And then r squares, right? So the objects are 1 meter from the axis, like r before squared. And there's two objects, right? 2 weights, right? So I'll multiply that by the 2. All right, so that is a number. I'm using general terms because everyone has a different number. And then multiply that by my omega before, which they give you. Mine is 0.69. And yours is a different number. So then you can use that to solve for your angular momentum before. And then our angular momentum after is our moment of inertia after, multiplied by our angular velocity after, which we don't know, right? The goal is to find our angular speed or angular velocity after we bring our arms in. So I after is going to be very similar. It's the student plus the stool. So 5 plus like the point masses, like m r squared. Now our r is different, right? R is after. And there's still 2 of them, so multiply that by 2. So that's a number. You'll get a number, right? My r after is 0.35. Yours is a different number. And then multiply by f. So then you'll set them equal to each other. So, right, that's a number. This is a number. This is a number. This is a number. So you don't know that. So after you set them equal to each other, right, you just do algebra. You can solve for your angular momentum after, right? You get a number, you put that into your question. The next part is to find the change in kinetic energy in the system. So then you gotta ask yourself, what types of kinetic energy do you have? Are you moving? No, right? We're in the stool, we're on the spot. Then are you spinning? Yes, because it says that we're spinning. So we only have rotational kinetic energy. So the change in kinetic energy is our kinetic energy rotational after minus our rotational kinetic energy before. So rotational kinetic energy is 1/2 I omega squared. You know your I's, right, before and after. You just found your angular velocity after, and they give you the angular velocity before. So then you'll just put it into the equation, and then you'll just do it. So our rotational kinetic energy after is 1/2. So I before, right? You solved for in the previous question, so whenever you did this, I guess your student and your stool may not be 5, and mine's 5, right? So whatever number that is, so it's 5 plus m r before squared times 2. Right, this is I before. Right, so you know that, and you know the angular velocity before, right? They gave it to you. And then you just found your I after, right? So my I after is student in the stool. Mine's 5. Yours is probably a different number. And then you know the radius, right? You solve for the angular or the moments of inertia in the previous steps. And then you just solve for your final angular speed. So you can find your kinetic energies. Oh, I guess I mixed them up. So beginning should be after and ending should be before, but it's it's the same idea. What's the negative number? Right, but you know everything. You just need to put it in the calculator and you get a number. Also, it is like embarrassing to the Hall of Fame process that Bill Belichick did not get in. Like, you win so many Super Bowls and you don't get in the Hall of Fame. Like, what do you have to do? Okay, so number 8. Yeah. Oh, this one's like the same thing, except it's a merry-go-round. And you're given revolutions per second, so you gotta turn that radians per second. So there's a merry-go-round. Alright, there's a guy. Here's the axis of rotation. I'll make it the center. So he is like 1.9 meters away. Here's the dude. He's 1.9 meters. He then walks to the center. you have to find his new angular speed. It's literally the same thing that you did before. So we'll do our before and after chart. So like L before is equal to L after. So L before, right, that is I before, omega before. So I before, now it's the merry-go-round plus the dude. So the merry-go-round, so I merry-go-round, I was right, M, plus I, maybe, I don't know, merry-go-round, I'll say MGR, and then for the man, IM, sure. But MGR can be a little confusing because it's like, we use whatever. It's the merry-go-round plus the person. So the merry-go-round is a solid cylinder. So the formula for a solid cylinder is 1/2 mr squared. Also, go Atlanta Hawks. So 1/2 mr squared. And then the person, we can treat the person as like a point mass. Oh, you gotta be careful. This is the mass of the merry-go-round. So my mass of the merry-go-round is 66. Yours is a different number. So maybe I'll do a specific. I'll call that like M1. It's like 66 is M1. Merry-go-round. So my merry-go-round is 1. I'll make my man 2. So plus the man. So we'll treat the man like a point mass. That's just M R squared, right? M2 is the mass of the man. My mass of the man is 74. Yours is a different number. And then R. So R, the merry-go-round, is the same. So I'll call that R1. So my R1 is the from my merry-go-round, which is 1.9. And then R2, right? That's like R for the man. My man is 1.9, so that's also 1.9, right? Before he is 1.9 meters away, so that's like R for the man. So then I know, right? You can calculate that. That's just a number. You can put it in your calculator, you get a number. And then our initial angular velocity, right? Mine's 4.6 revolutions per second, but we want our angular velocity in radians per second. So you have to convert that revolutions per second to radians per second. So then the way you do that, I'll do that over here. So 0.46, mine's 0.46, yours is a different number, revolutions per second. We want radians per second. So we want to divide by revolutions, and we want radians. So 1 of revolution is 2 pi radians. So I'll just multiply my revolutions per second by 2 pi, and then I will get radians per second. So then you'll know that, right? So then you'll calculate it. It's just a number. So that's L before. And then L after is going to be I after, omega after, which we're solving for omega after. So I after is the same process as the merry-go-round plus I for the man. And the merry-go-round is going to be the same, right? It's still 1/2 M merry-go-round R merry-go-round squared. But now the person moved. Now he is 0 meters from the center. So that means now his person R is 0. So then if we add mass of the man, R, now I guess I'll call it like R0, right? R0 is 0, so that's all gone. So the moments of inertia after is just the merry-go-round. So you'll do that, get a number, and then you'll know L before is equal to, right, I after, omega after. Right, you know this, right? You know this, so that you can just solve for omega after, right? You can do algebra, get a number, put it into Quest. And then the second part, part 9, is just like what we did in the previous question. We found the chain of kinetic energy. So that is K rotational after minus K rotational before. That's an R. And so then you'll do 1/2 I after omega after squared minus 1/2 I before omega before whole thing squared, and you'll get a number, and that number will be your answer you'll put in the Quest, right? You know everything. We just solved for the I after, right? It's like this is I after, right? You solve for omega, I guess I start with the wrong thing. But like you know I after, right? You know omega after, you know I before, you know omega before, so then just like put it into your calculator and you can solve for the change. Okay, number 10. This one, hopefully we've done a learning calculus, and right, you know that L before is equal to L after. So then I omega before equals I omega after. And if you pull in her arms, right, that means that after her moment of inertia goes down, which means to keep angular momentum conserved, her angular velocity has to go up. And so that one will be choice number 2. All right, there's no air friction, so it doesn't really do anything. So it's not 1. It's not 3 because angular momentum conserved. It's not 4 because there's no net torque, nothing's pushing on her. It's not 5 because she's not changing any height, so there's no changing potential energy. It's not 6 because there's nothing pushing on her. Okay, so you gotta choose a true statement, and we know that when she like does it takes energy to like pull in your arms. So like she's doing work. So that's number 2. All right, number 1 is not true because like her kinetic energy increases. Number 3, angular momentum is conserved. Number 4, where when we pull in her arms, our moment of inertia decreases. So that's not it. Number 5, right, rotational energy is not conserved, so then you go faster. Number 6, there's no rotational potential energy. It doesn't exist. I don't know what that is. So that's number 11. The learning calculus will hopefully help you with those 2 questions. Okay, the last question. I kind of started it, but let's reverse it so I can start over. Okay, so this one is like your, it's like a balance beam. Maybe you use them. I learned how to use them in like 4th grade. I don't know if people still do them, but it's like kind of like a triple beam balance where you'll have the fulcrum. If you do it right, the fulcrum's in the middle, then you'll have your like node mass on this side, or on one side. I'll put my node mass on the other side, so they can measure the unknown mass, and you'll use that to see like how much gold you have or something. Okay, but if you're a shopkeeper and you want to like rip off your customers, you'll just move the fulcrum, right? So if I'm selling gold, then I want them to think that there's more gold than there actually is, so that they will pay me more money, even though I'm selling them like less gold, right? If I'm selling them like 100 grams of gold, but I'm charging them for like 110 grams of gold, then they're getting ripped off and I'm making more money. So if I want my known mass to be more than my unknown mass, so I'll just shift my fulcrum over here, so that, right, because you know from like the balancing being acts, you're like your M1 R1 is equal to like M2 R2, so that my R2 goes down, which means I have to put my more mass in there, so that means it looks like there's more than there actually is on the other side, right? That's not ripping you off. I'm charging you for 110 grams of gold when there's actually like 100, because I'm putting like 110 grams here, but there's only 100 over here, so you're getting ripped off. And we want to find out how much the shopkeeper is like screwing with the weight of the goods. So we'll just move the fulcrum closer to the known side, and it tells you the distance, and I'll call that x. Okay, so if I got my picture, the 2 pans, mine is 46.1, yours is a different number, I'll call that D. D. And then the distance from the center mass, right, the shifts, I will call that X. Okay. So if we do our balanced torques equation, right, the torque from the unknown mass has to equal the torque from the known mass. So technically the force of gravity, so it's already perpendicular. So then the force is just m. So I'll do mass of the unknown times little g. And then the r, right, is, so normally it'll be the center of mass, but now we move the fulcrum so that it's over here. Oh, maybe I'll do it in a different color. It's in red. So now it's, right, this is the, so right here is like d over 2. So the distance away from the fulcrum is d over 2 plus x. And then the torque on the other side is the mass of the known. So I'll do like mass of the known, I'll call that J, K, times little g, its weight, multiplied by like its distance away. So if like the whole thing is like d over 2, I shifted over x, so now it's like d over 2 minus x, right? If we lost like that distance, it's that distance closer to the fulcrum. So this side, oh, the maps are not good. So the r is now d over 2 minus x. Okay. The g's can cancel out. So it's the mass of the unknown, d over 2 plus x, is equal to the mass of the known times d over 2 minus x. Okay. Right, that's a u, not a 4. That's a u. Okay, so the way like I do it, I like to like make up a number for my unknown mass and see how much my known mass has to be to get balanced. So if I make my like, I'll just solve from, so if I make this like 100, right, I'll get a number on this side. So like my d is 46.1, my x is 1.59. I solve for my known mass, 46.1 over 2 minus 1.59, right? Then you can compare and see like what percent you're getting ripped off by. So if I put that in my calculator, whoa, they changed the UI in this. Okay, so on this side, I'll do 100 multiplied by 46.1 divided by 2 plus 1.59. And then on this side, right, 46.1 divided by 2 minus 1.59. And then I'll divide. I get my known mass as 114.818, whatever, 0.818266. The units don't really matter. Let's say it's grams. So my unknown mass is 100 grams. Oops. So that means my known mass is like 114. So that is what, 14.81 whatever. So I would divide that by. So if you do your known mass divided by your unknown mass, that's like the fraction getting ripped off. So you can convert that to your percent. So like then you multiply that by 100, and that is how much the shopkeeper is ripping off the person. So if I divide this by 100, and then we're, wait, it's 14%. So if it was 100, then I'm charging you like 14% more. So like, I guess you subtract some known mass minus unknown mass. So because it's like 14% more than multiplied by 100, that is like your percent that you're getting ripped off by. So if I do that minus 100, yeah, then that's my answer that I'll put in the quest. Right, because my known mass is 114, or it's 115, but my unknown mass, what you're putting on the other scale, is 100. So it looks like they're supposed to be equal. So it looks like you actually have 115 grams, but you don't. So I'm ripping you off. And that's the homework.